Hey, geographers, it's Angela here with another lesson in physical geography. And in this lab, we're going to be focusing on water resources. And every time that we face or we come into contact with a new lab in physical geography, it's important to go back and center yourself in which sphere that we're talking about, which cycle. The Earth functions in cycles. So we've talked about the lithosphere, and now we're moving into the hydrosphere. Hydro meaning water. Water is a resource that we're given. It's something that we use as humans. It's something that we're actually made up of as well. And it's also something that other living things around us rely on for survival. So this is a resource not to be taken lightly at all. It's also a resource that is given not in equal distribution across the globe. So, for example, if you're living in Southern California, it's a resource that is actually not provided for the amount of people that live in Southern California. Majority of the water for the humans in Southern California comes from aqueducts that are built from hundreds of miles away. So when we say that water is a resource and it's not to be taken lightly, it's very serious. So you've likely heard before that there is more water on earth than there is land. That is true. Majority of that water, a large majority of that is salt water. In fact, 70% of the earth's surface is covered by water. Water is a universal solvent. It is called a universal solvent because it's capable of dissolving more substances than any other liquid that we know on earth. And it's water's chemical composition and physical attributes that make it this excellent solvent. For example, think about when we dissolve salt into water, when we dissolve sugar into water, and other substances. Water is important to every living thing on earth. It means that wherever water goes, either through the air, the ground, our bodies, it takes along chemicals with it, minerals, and nutrients. So it's important to remember that since water is a solvent, there are going to be other things present in the water because water, being that universal solvent, means that, for example, there could be great things in there for humans, like helpful minerals. Unfortunately, there might also be things like fake fertilizers, like lead, like things that we as humans put into our environment, and along the way, water picks it up and then we ingest it. So, in part A of this lesson, we're going to talk about the basics of the hydrosphere. And we've learned there are four main spheres: the biosphere, the atmosphere, the lithosphere, and the hydrosphere. And all of these interact with one another. For example, when we talk about the hydrosphere, it also includes the atmosphere. There's always water in our air. Although we can't see it, it's there. And it's expressed as humidity. Water exists in three states: as a solid, a liquid, and a gas. So, in addition, water does not only exist as fresh water, but also as salt water. In fact, the percentage of fresh water is significantly lower than the percentage of salt water, which means the amount of fresh water available for human consumption is really low. Out of all the water on Earth, only 2.5% of it is fresh. That's it. Even though a majority of the earth is made up of water, only 2.5% of that is fresh water and ready for human consumption. Of that 2.5% of fresh water on planet Earth, a majority of the fresh water is held in glaciers as frozen water or frozen snow and as groundwater. So most fresh water does not come from rivers and lakes. And here is a small diagram showing you all the places in which water lives, interacts, and includes the four spheres of the earth. Water cycles through the earth, and it's something called the hydrologic cycle. Now, when we were younger, we called it the water cycle. Well, now we're in university, we're in college, so we call it the hydrologic cycle. And like energy, water cannot be created or destroyed. It simply changes form. In fact, the very first water ever to exist on Earth is still here today. Water moves in a variety of ways throughout the hydrologic cycle. It's evaporated by using the sun's energy from oceans, lakes, streams, surfaces, and reservoirs, and through transpiration, a process in which water leaves a plant through its leaves. So plants, any trees, any plants that we use to eat or grow, or um, any plant that might be in your yard, when it breathes, and plants breathe, because remember, they breathe in carbon dioxide and they breathe out CO2, and we as humans do the opposite. We breathe in oxygen and we breathe out CO2. And when plants breathe, as with humans, we actually need a little bit of water in the air. And same with plants. When they breathe out, they actually breathe out a little bit of water as well. So remember that evaporation occurs when water changes from a liquid to a water vapor. So that's like a gas. The combination of these two processes is called the evapotranspiration and accounts for water that leaves the surface of the earth. And as water evaporates into the atmosphere as gas, it cools and condenses into a process called condensation. Condensation occurs when water vapor then, once in the air or in the atmosphere, changes back into a liquid and it falls back down to earth in a process called precipitation. Precipitation. Precipitation could mean snow, sleet, hail, or water. Once the water reaches the surface of the earth, it runs as runoff. It can either run off along the surface, soak, or infiltrate into the ground. And when it infiltrates in the ground, we call this groundwater flow. Water that does not infiltrate into the ground is called runoff. Water that enters into the ground through a process called infiltration and it moves into the soil through a process called percolation, and then it's stored underground within the rock or rock spaces, and this is called groundwater and aquifers. One of the first things you're going to do in your lab is use this diagram to fill in A through I and go through the process of using the terms that I've just gone through and fill in using the bolded terms into each of these slots. So for a minute, try to think of what word would you put in for A? Come back up here and choose. Which one would you put for A? Now, if it were me, I would put precipitation. Let's scroll back down to our diagram here and let's come to the letter F. What would you put for the letter F? Let's talk about the distribution of water. Water is not available in equal amounts all throughout the globe. There are some parts of the world that have a lot of water and other parts of the world that don't. For example, in California, Northern Californians don't really like Southern Californians that much because guess what? We take their water. The state of California has built aqueducts, which are pretty much fake cement covered rivers that bring water from places that have water to places that don't have water. So figure 8.3 shows the distribution of water on Earth. And as you can see, only 2.5% of water on Earth is fresh. And of that amount, 30% of it is in the ground. So that means 0.08%. So less than 1% of all water on Earth available to humans as fresh water for irrigation, drinking, and sanitation. This means that as humans on Earth, all we have at our disposal is less than 1% of fresh water. Water is stored on Earth in 5 main reservoirs: oceans, glaciers, and ice caps, groundwater, surface water. Surface water includes waters in lakes, rivers, and soil, and atmospheric water, water that's in the air. So here is a representation on the left-hand side that says total global water. All of the global water here is represented. And in green, you'll notice that 96.5% of our available global water is in the ocean, which means that 2.5% of it is fresh. Of that fresh water, most of the Earth's fresh water, 68.7% of it is in glaciers and ice caps. So it's frozen. It's not able to be used. And then 30% of that 2.5% is underground. 1.2% of that is on the surface. And of that 1.2%, most of it is frozen on the surface. 20% of that 1.2% is in lakes. And then you've got other small percentages here. According to the U.S. Geological Survey, there's approximately 326 million cubic miles of water on Earth. And this distribution is shown in this table, Table 8.1, the sources of fresh and salt water on Earth. And again, we're shown that majority of the water we have on Earth is salt. And then in cubic kilometers, it's showing us where all of our fresh water is held, most of it in ice sheets, glaciers, and frozen. So now that we realize that the amount of fresh water around the globe is not given in equal amounts, well, let's figure out how humans use the water. Because take, for example, Southern California. That is a place that has not given a lot of water, yet a lot of people live there. So how do people there use their water? In Southern California, a majority of the water used is for grass. It's for lawns. So as we can see from the above tables and information, there's a minimal amount of fresh water available for people. And this distribution changes over time and depends on the climate. For example, our Earth is in a warming trend, and more water is stored in the ocean as salt water. And as the Earth cools, more water is stored in snow and glaciers. Currently, the Earth is experiencing a warming period, and so the snow and glaciers and ice sheets are melting and draining into the sea. So that means that the amount of fresh water that we have is being lost to the ocean. So we have a decreasing amount of fresh water available to people. And as this amount of fresh water actually is not frozen, right? It becomes liquid and decreases, our human population is actually increasing. So we have a global demand for water. In this graph right here, you're going to be reading about how the population of people on Earth has risen in the last 120 years. So at the bottom of this graph is the year 1900. And at the far right hand side of this graph, you have the year 2020. So this graph represents 120 years. So you have an increase in billions of people over 120 years, and we have a supply of fresh water that's decreasing. So this figure provides basic statistics for population, and it's useful for determining what a population is going to look like on a planet. But however, in order to plan sustainably to mean that we have enough resources on Earth for all the humans that we have, and to ensure that we all have access to resources like water, it's important that we look at factors that of how water is used and where, because not all humans use the same amount of water. So the distribution of water varies globally, and in order for us to manage our water supplies, it is important we understand how this water is used. One way to geographically display information is use of a cartogram. This image below, figure 8.5, is a cartogram. It is a map that looks a little wonky, doesn't it? It looks really out of proportion. What it is showing you is the use of water by certain populations. So countries that are look a little bit larger and a little bit chubby means that they are using larger amounts of water. You'll notice here that the lower part of the continent of Africa is pretty much gone. That's because the amount of water that they're using is so minimal. Where you look at populations like the United States and population like India, and these countries seem blown up because they're using a large amount of water. So their size represents the use of water. Now we have a cartogram that's going to represent population. China has the world's largest population, followed by India. The United States, actually the third largest population, but China has actually 8 times the amount of people as the United States. China, India, and the United States use the most water, but they are also the three places on Earth where most people live. But water use per person is about 3 times higher in the United States than it is in India and China. So, as I've said, China has 8 times the amount of people as the United States, but yet in the United States, we're using 3 times the amount of water. While everyone needs water, the quantities used varies widely. On average, people in Central Africa use only 2% of the water used by each living person in North America. So if you can imagine, on average, people living in Central Africa use only 2% of what we use as an individual in North America. 2%. I don't know, if I went out to pizza, would you want 2% of a pizza? No. Figure 8.7 maps countries per capita, which means per person, measured by cubic meters per year. And this includes water withdrawals for agriculture, like your lawns or food, industrial and household and public services. So this is going to show the amount of water that's taken out per person as of 2005. And obviously the largest, we're going to see places like you down here, we've got Chile, Argentina, Australia, United States, and Canada. We've got places over here. Obviously, we're looking at these are desert regions as well. What spatial patterns do you notice on this map? Which regions have the most water withdrawals and which have the least? Explain your response, and you're going to be doing that in your lab. Now, let's try to focus on water use in the United States. So, If in the United States we're the population that uses the most water per person on earth, what are we doing? Let's take a look about how we use water in the United States. So 87% of the water used in the United States is fresh water. The remaining water used is salt water for the ocean from the ocean. So according to the USGS, the United States used 322 billion gallons of water in 2015. And the distribution is shown on this map. So the distribution of water in the United States was highest in places like California and Texas. In your lab, you will be explaining which states use the most water and which states use the least water. In this figure below, we notice that in figure 8.9, it shows the distribution of how this water was used. We have 7 categories that were selected for the top usage. So if we scroll down, we're going to notice that the second largest use of fresh water in the United States was used for plant growth. This is for our food. This is also for our lawns. This is for agriculture uses, including chemical application, crop cooling, and harvesting. Irrigation is also used for golf courses, cemeteries, nurseries, and parks. You'll notice that the largest was for thermoelectric power, and this is for electricity. Now that we realize that a majority of our water actually comes not from the surface, but from the ground, let's learn about how once we receive that water, what happens to it. One of the main terms that we need to utilize for this part of the lab is the term watershed. What is a watershed? A watershed is a natural drainage. So think about, for example, when you do the dishes or when you're outside and you use water. Where does it go? Well, some of it drains out into the street. Some of it soaks into your lawn or maybe into some sort of open area that you have. Wherever water goes, it's going to either drain somewhere or it's going to evaporate. So a watershed is the area of land where all that fresh water falls. It's a natural drainage. Just like the water in your yard or sink must drain, so too does the water in our environment. All water drains to somewhere, is used, or evaporates. Every single human lives within a watershed. Watersheds exist everywhere, and everyone lives within a watershed. So, for example, if you live in the valley, the San Fernando Valley, the watershed that you live in is for the Los Angeles River. All of the water that falls there is captured, or if you decide to put in some toxic chemicals, that natural drainage area flows into the Los Angeles River. Now, if you live somewhere like in Orange County, chances are that your watershed is the Santa Ana River. And if you live somewhere along the freeway, like in Hawaiian Gardens or Lakewood, chances are that you are in the San Gabriel River watershed. Notice that in figure 8.10, which is below, I'm going to show you in a minute, elevation does play a role in where water drains. Gravity pulls water toward the center of the earth so that water at higher elevations will drain naturally to lower elevations. So that means that all of the water that falls on top of a watershed will flow or seep into the ground. And then we'll notice how this happens in figure 8.10. We receive water through precipitation. That might be snow, that might be rain, sleet, or hail. All the water that falls within this lighter green area is within this particular watershed. This watershed includes the surface of the earth. It also includes the underground portion as well. Because this water might drain on the surface of the earth, it might become evaporated, or it might infiltrate and percolate and recharge our groundwater, which remember, most of our fresh water on earth is either frozen or in the ground. Watersheds are divided into hydrologic areas, and we in parentheses HA, and they're given distinct numbers. And each hydrologic area will contain unique land uses. Because wildlife and people depend on water for survival, it's important that watersheds are monitored for water quality. This is very important. For example, the city of Pasadena relies on mostly groundwater. They live right at the bottom of the San Gabriel Mountains. There was a company that made jet fuel. They rinsed out their large cans of jet fuel and dumped that into the water. The remnants of those chemicals mixed with the water, because water is a universal solvent, soaked into the ground. And since the San Gabriel Valley, people who live there utilize mostly groundwater, that water came back up and was used by residents, and it was laced with jet fuel. It's very important to monitor what we're putting in our water, because that water soaks into the ground and then we use it. All components of the hydrologic cycle have an impact on water quality and watershed, and one of these is water quality is runoff, which is determined by the relationship between precipitation and infiltration. The amount of water that is soaked into the ground depends on the porosity of the soil. Some soils can soak in water very easily. Other soils, like clay, repel the water. For terms of this, we use a word called permeability. This is the ability of water to flow through soil. Some rocks are permeable, which means that water can flow through the ground. Other rocks are impermeable, which means that when water hits that rock, it's repelled away. So it's important to understand that different kinds of soil are going to interact with water in different ways, which means that different parts of the world are going to store water. For example, some places in California and some places in Oregon, depending on where you live, city by city, location by location, are going to be able to pull up water from the ground. For example, for a well, for a city, or for a town. And if they have groundwater that's able to be stored, it means that they have rock that's more permeable and more porous. So now that we realize that every location on Earth receives different amounts of water, manages it differently, and has different storage capabilities within the ground, how do we manage this? So federal, state, and local jurisdictions manage and monitor and regulate our water. So in 1972, we enacted the Clean Water Act, and it established the following: that we have a basic structure for regulating pollutant discharges in waters in the United States. And it gave the Environmental Protection Agency the authority to implement pollution control programs. And it's important to maintain our requirements for water quality standards. And it made it unlawful for persons to put any pollutants into any of our water sources. Under the Clean Water Act, California identifies more than 860 water quality monitoring variables, and this includes contaminants. In Table 8.2, it provides an overview for some of those indicators. Let's go ahead and scroll down and look at them. On the left-hand side, you're going to look at indicators. In the middle column, we're looking at sources. And on the right-hand side, we see the impact. So if any of these indicators get into our water, into the sources here, this is what will happen, the impact of what will happen. So for example, if we get anything like metals or metalloids, including lead, mercury, and selenium, this can be harmful to human health, particularly child development, and have been known to cause cancer, organ damage, nervous system damage, and death. How about sulfates? Sulfates come from discharges from industries, sewage, tanneries, pulp mills, and may cause intestinal issue in mammals, which means humans, guys, because that's us. What you're going to be doing for this lab is going in and looking at your waterway. You will click on here, you will say where you live, and then you're going to answer questions based on what you have found from where the water where you live. Now it's important to learn about our water budget. Well, we've already learned that Americans use the most water on planet Earth. So how should we use it? So in order to manage our water supply, we need to understand how much water enters a watershed, how much is processed, how much leaves, and then how much water leaves the actual watershed. This information is provided in a water budget. A water budget calculates the total inputs and outputs. This is helpful because we need to figure out how to manage our water. Water budgets are going to vary based on location, soil, climate, and land use. How we as humans decide to live on that piece of land. After all, Southern California, we don't receive enough water for the amount of people who live there. So what do? We bring it from somewhere else. So in order to calculate a water budget, we need to know the factors that influence water movement. So we have our field capacity. This refers to the total amount of water a soil can hold. Different soils, as we've heard, have different porosity levels and different permeability levels. So different soils hold water in different ways. Then we have water that is lost to evaporation. This depends on the overall temperature. This is where sun's rays and solar radiation comes into influence. Places that live near the equator or have lower latitude numbers are going to have stronger amounts and more concentrated solar radiation, and therefore higher amounts of evaporation. We also have water that's lost to evapotranspiration. This means that precipitation is the amount of water that enters the watershed from the sky, and this will determine the actual evapotranspiration. If precipitation decreases in a system, there is less water available for evapotranspiration. Evapotranspiration is present when we have plants involved. At the end of a month, once the AE, which is actual transpiration, and PE, which is potential evaporation, are known, the amount of water remaining in the soil shows how much water the soil will have over time. Now, if we have more than we need, we're going to have a water surplus. And if we're using too much, we have a water deficit. So in Southern California, we have a perpetual water deficit. Many cities in California don't rely on local water supplies. In San Diego, 85% of water supplies come from outside the local area. And figure 8.15 shows the major surface water regions for California. Down here, you will notice this is a map of California, and in blue, this is a net importer of water. So this means that all of the areas that are shaded in this blue actually bring in their water from other areas. How do they do this? They do this from canals and aqueducts and pipelines. You will notice this cross-hatched black that shows how Southern California receives its water. It takes it from the San Joaquin River here, here, and here. And then we have, as humans, built these fake waterways, and they lead all the way down here to Los Angeles, and then all the way down here to Southern California.